So the last thing that we want to do is to try to compute the area between two curves. So far, all we've really tried to do is find the area between a particular curve f and the x-axis. But what if we wanted to find the area that was trapped between two curves? And just to be clear here, when we talk about the area between two curves, we don't mean signed area anymore. So we would consider, if these were our two curves, all of this to be positive area. Right? We just want to know what's the total area that's trapped between these two curves here. So let's assume that f and g are two continuous functions over some interval a, b, and that one of your functions is above the other function on that interval. So in this case, between a and b, the function g of x, that's the one that I've highlighted in purple, is on top of the function f of x. If we want to find the non-signed area between those curves, well, this is what we can do is we can take the function g of x minus the function f of x and just take the definite integral of the difference of these two functions from a to b. And remember, we talked about the different properties of integrals. This is like saying the integral from a to b of g of x minus the integral from a to b of f of x, right? But it's often just quicker to subtract the fractions first and then just do one antiderivative instead of doing it twice. So why is this the case? Well, I've tried to sort of highlight to give you a sense of why this happens. If we were to look at the integral from a to b of just the function g of x, so this part here, we get this purple part here, except technically we get a little bit of extra stuff, because if we're going all the way from a to b, we would also be including this area right here, right? Similarly, if we were just to take the function, or just to take the definite integral from a to b of f of x dx, we'd be getting the area between the f curve, that's the green one, and the x-axis over that interval. But again, we'd be missing a little bit of stuff, because between this f curve and the x-axis, we'd also be getting this little space right here. Since we're subtracting these two, this extra space, which we don't really want to include because it's not trapped between the two functions, it'll cancel each other out, and that's why we don't really have to worry about it. All right, and so it turns out that what we can do, when we subtract them, because right, we want this area, this green area underneath here, to be positive. And if we were to compute this integral f of x dx on its own, it would be negative area because it's underneath the y or the x-axis. So if we subtract it, it'll become positive, and it's really like we're sort of adding these two integrals together in a sense. All right, so let's do an example to try to figure out the area between two curves with some specific functions here. So let's take the function f of x equals x squared minus 2 and the function g of x equals 6 minus x squared, and we want to find the area between these two curves. All right, let me start by drawing the function f of x. X squared minus 2 is a parabola that's been shifted down 2 units, so it looks something like this, roughly. And the function g of x, 6 minus x squared, that's like negative x squared plus 6. That's a parabola that's been flipped upside down because of the negative, but then shifted up 6 units because of this plus 6. So that's going to look like this. Something like that. We want to know the area between these two curves. So essentially what we're looking for is this area here. And according to this theorem up here, I can do this by taking the definite integral of the top function, whichever function's on top here, which for us is the g of x function, right? That's the one that's on top. So g of x minus f of x dx, right? Which is going to be g of x, that's 6 minus x squared, minus f of x, which is x squared minus 2, dx, which is going to be, if I were to simplify this, I have 6 minus x squared minus another x squared, and then plus 2 when we distribute the negative sign. So that's a positive 2 and a positive 6. That makes 8 minus 2x squared dx. 2x squared because we had a negative here and a negative here. Now, I've left out all my bounds here because I don't actually know what my bounds are just yet, right? These functions are definitely going to intersect somewhere, but I'm not sure right off the bat what exactly my a and my b are here. What are these? That's what I want to figure out. Those are going to be the bounds on my integral, but I have to figure out what those are. So how do we figure out where these two curves intersect? Well, the curves are going to intersect when their outputs are equal to each other. So in other words, where is f of x equal to g of x? If we know that, then we'll know exactly where these curves intersect. And for those x values, those are going to be the bounds on your integral. So I just need to take my function f of x and set it equal to g of x and solve. When is x squared minus 2 equal to 6 minus x squared? All right, to solve this, I'm going to add x squared to both sides. So I get 2x squared minus 2 is equal to 6. Then I'm going to add 2 to both sides, so I get 2x squared is equal to plus 2. We get 8. Then I'm going to divide by 2. Okay, so x squared is equal to 4. And now I know that the solutions to this are just positive and negative 2. Awesome. That's where they intersect, at negative 2 and positive 2. So what I can do is I can take the definite integral between negative 2 and positive 2 of this function g minus f. And we had found that function to be 8 minus 2x squared dx. Luckily, by the fundamental theorem of calculus part 2, this is an easy computation. The first thing that I'm going to do is find the indefinite integral of this function. So find the antiderivative of 8 minus 2x squared dx. So that's going to be antiderivative of 8 is 8x. And the antiderivative of negative 2x cubed would be negative 2x squared. So we add 1 to get x cubed and multiply by 1 over the new exponent plus a constant. Right, so my antiderivative function, big F, is going to be 8x minus 2/3 x cubed plus a constant. Constant's going to disappear when we get to step 2, which is to take this antiderivative function, evaluate it at the endpoints, 2 and negative 2, and subtract. So this is going to be, when I plug in 2, I'll get 8 times 2 minus 2/3 times 2 cubed. The plus c is going to go away. Okay, that's big F of 2. And I need to subtract big F of negative 2. Okay, I need to plug in negative 2 into this function. So I'd get 8 times negative 2 minus 2/3 times negative 2 cubed. So this is going to be 16 minus 2/3 times 2 cubed would be 2/3 times 8, which is 16 cubed. And then we'll subtract, parentheses, 8 times negative 2 would be negative 16, minus 2/3 times negative 2 cubed, which is negative 8. So negative 2/3 times negative 8 would be positive. 8 times 2 is 16/3. All right, and then you need to actually compute this, and you get 16 minus negative 16 is like 16 plus positive 16, which would be 32. And then we'd have negative 16/3 and another negative 16/3, so minus 32/3. I don't know. Compute that if you want. You'll get a real number, but for our purposes, this is good enough. That's the area that's going to be trapped between these two curves. Okay, so just to summarize, what we did is we determined which function was on top. That's going to be the g of x function, 6 minus x squared. So we subtract g of x minus f of x, right? G of x minus f of x. And we figured out where these two functions intersected by setting them equal to each other and solving, and those told me what the bounds were on the integral. And then I just applied the fundamental theorem of calculus, part 2, to actually compute that integral. So let's do one more example. Let's find the area between sine of x and cosine of x on the interval from pi over 4 to 5 pi over 4. Oof. Okay, well let me start by drawing sine of x. And I'm not sure which function's on top here, so I'm just going to start with sine of x here. And I'm only really interested from pi over 4 to 5 pi over 4, so I don't have to keep drawing it on the other side. Right, this is 2 pi, so it's further along than we really need to go. This is pi over 4. Oh, sorry, this is pi over 2. So that's pi over 4, 3 pi over 4, and this is going to be 5 pi over 4. Okay, so this is the function sine of x, and then cosine of x starts up here at 1, and it's going to intersect this curve at pi over 4. So it comes down like this. Gets down to -1 here. Then it comes back up again and intersects this curve again at 5 pi over 4. Right, so cosine would end up coming back up. Right. So cosine looks something like this. I didn't draw it super well. Right? But these two functions do intersect at pi over 4 and at 5 pi over 4. And so we're just looking for this area right here that's trapped between them. So which function is on top here? Right, your top function is going to be the purple one. Whichever one the purple one is, that's the one that's up above, below the green one. And so that's going to be the function sine of x. So here, my top function is sine of x, and my bottom function is cosine of x, at least on this interval, right? After that they switch, but on this interval, sine of x is the top and cosine of x is the bottom. And so what we need to do here is find the definite integral on the interval from pi over 4 to 5 pi over 4 of the top function minus the bottom function. So sine of x minus cosine of x dx. And this is as simple as using the fundamental theorem of calculus. So remember that the first step here would be to take the antiderivative of this function. Okay, so the antiderivative of sine we said was negative cosine, and the antiderivative of negative cosine is negative sine. And there's a plus c, but that's going to go away when we do when we plug in the bounds. So now step 2 is to take that antiderivative that we just found, that big F of x, and evaluate it at the endpoints of our interval. So 5 pi over 4 and pi over 4, and then subtract them. Right, so what we're doing here is we're taking this whole function, plugging in 5 pi over 4, then plugging in pi over 4, and subtracting them. So first we have negative cosine of 5 pi over 4 minus sine of 5 pi over 4. Right, that's big F of the first bound minus big F of the second bound. So negative cosine of pi over 4 minus sine of pi over 4. Almost out of space. And remember, the plus c goes away when you're doing a definite integral. And so this is just as simple as actually plugging in everything in. What are these numbers? Well, use the unit circle if you need to. Remember, if this is a unit circle, pi over 4 is here, and 5 pi over 4 is down here. This is square root of 2 over 2, square root of 2 over 2, and this is the same but negative. Okay, right? So plugging everything in here is as simple as just using the unit circle to evaluate this. Change color so you can see it better. So negative cosine of 5 pi over 4 would be the opposite of cosine of 5 pi over 4. So the opposite of negative square root of 2 over 2 minus sine of 5 pi over 4, so minus negative square root of 2 over 2. Okay, then we'll subtract the opposite of cosine of pi over 4. Cosine of pi over 4 is square root of 2 over 2. Minus sine of pi over 4 is also square root of 2 over 2. And when we simplify this, we get these turn positive, these turn positive. So this is just square root of 2 over 2 plus square root of 2 over 2. That's 2 copies of square root of 2 over 2, which is just plain square root of 2. Minus negative square root of 2 minus square root of 2 would be negative square root of 2. And again, these negatives will cancel out, and we're just left with 2 copies of square root of 2. So that's going to be the area between these two curves. Okay, so this highlighted area here, unsigned, would be 2 square root of 2.